October 24, 1944. The Sibuyan Sea, Philippines. Dawn broke over a Japanese naval task force steaming toward its destiny. The largest concentration of Imperial firepower assembled since Midway. Battleships Yamato and Musashi, their 18-inch guns capable of hurling shells the weight of automobiles to distances beyond the horizon, accompanied by cruisers and destroyers in a formation that stretched across miles of ocean. On the bridge of the heavy cruiser Maya, Lieutenant Commander Takeshi Nakamura stood at his radar intercept station, headphones pressed against his ears, listening to the electromagnetic whispers that filled the airwaves. The equipment before him was Japan's most advanced electronic warfare system, designed to detect enemy radar transmissions before visual contact, giving Japanese commanders precious minutes of warning before American aircraft arrived. But on this morning, something was wrong. The signals flooding Nakamura's receivers were unlike anything he had encountered in 2 years of monitoring American radio frequency emissions. They were constant, powerful, operating on wavelengths his equipment could barely process. The pulses came from multiple directions simultaneously, overlapping and interweaving in patterns that suggested a level of coordination his training had never prepared him to interpret. He adjusted his direction-finding antenna, trying to isolate individual sources. But the signals were everywhere, ahead of the fleet, to port and starboard, even behind them where no American ships should be. Nakamura reached for the communication tube connecting his station to the Combat Information Center. His hand hesitated. What he needed to report defied the logic of naval warfare as Japan understood it. The signals indicated that American ships were tracking the Japanese fleet continuously from distances of 50, 60, perhaps 70 miles, ranges at which no optical system could function, at which Japanese reconnaissance could not even confirm enemy presence. The implications were devastating. If the Americans could see in darkness, through weather, across distances that rendered Japanese lookouts blind, then every principle of naval tactics that had guided the Imperial Navy since its victories over Russia 40 years ago had become obsolete. He pressed the button. Combat Information Center, this is radar intercept. Multiple enemy surface search transmissions detected. Bearing 045 to 180 degrees. Estimated range 60 to 70 kilometers. Signal characteristics consistent with American SG and SK series radar. Recommend immediate alert status. There was a pause. Then the voice of the watch officer, edged with something that might have been fear. Confirmed. All stations report enemy radar contact. They know exactly where we are. And in that moment, listening to the steady electronic pulse of American radar, painting his ships with invisible light, Takeshi Nakamura understood that the Imperial Japanese Navy was steaming into battle against an enemy that could see them perfectly, while they remained effectively blind. And that this asymmetry would determine not just the outcome of the coming engagement, but the entire course of the war in the Pacific. To understand the magnitude of what Japanese radar operators discovered at Leyte Gulf, one must first understand the divergent paths of radar development taken by Japan and the United States in the years leading to October 1944. Japan had not ignored radar technology. As early as 1936, Japanese naval researchers had experimented with radio frequency detection systems, and by 1941, several radar types were in limited service with the Imperial Navy. The Type 21 air search radar could detect aircraft at ranges approaching 100 kilometers under ideal conditions. The Type 22 surface search system could locate ships at distances up to 30 kilometers. These were respectable achievements for their time, representing genuine scientific and engineering competence. Japanese physicists understood the principles of radio wave propagation. Japanese engineers could manufacture the magnetrons and waveguides necessary for microwave transmission. But Japanese radar development had been constrained by factors that would prove decisive at Leyte Gulf: limited industrial capacity, conservative naval doctrine, and most critically, a fundamental misunderstanding of radar's role in modern naval warfare. The Imperial Japanese Navy had approached radar as a supplement to traditional methods, optical rangefinders, sound detection, and most importantly, the superbly trained lookouts who formed the backbone of Japanese naval reconnaissance. Radar was considered useful for extending detection range in poor visibility, but the fundamental architecture of Japanese naval operations remained rooted in visual confirmation and manual fire control. Japanese radar systems were designed to detect targets, not to provide continuous tracking data for weapon systems. They reported presence and approximate bearing, but lacked the precision and update rate necessary for fire control integration. American radar development, by contrast, had evolved from an entirely different operational philosophy. Following the technological exchange with Britain in 1940, which brought cavity magnetron designs to American shores, the United States had embarked on a radar development program of unprecedented scale and ambition. The MIT Radiation Laboratory, established in November 1940, had coordinated the efforts of hundreds of physicists, engineers, and mathematicians from universities and industrial laboratories across the nation. The mandate was clear: develop radar systems that could be integrated into every aspect of naval operations: navigation, fire control, fighter direction, and, most crucially, provide continuous situational awareness that would allow American commanders to fight effectively in conditions where Japanese visual superiority was negated. The result was a family of radar systems that transformed American naval capabilities. The SG surface search radar, operating at 3,000 MHz, could detect ships at ranges exceeding 40 kilometers with sufficient precision to generate accurate firing solutions. The SK air search system could track aircraft formations at 150 kilometers. The Mark IV and Mark VIII fire control radars could lock onto targets and provide continuous range, bearing, and elevation data directly to gun directors, enabling accurate fire in total darkness or through smoke and rain that rendered optical systems useless. But individual radar performance told only part of the story. What truly separated American from Japanese radar capabilities was integration. American radar systems fed data into centralized combat information centers, where trained operators maintained comprehensive tactical pictures, coordinating fighter direction, anti-aircraft fire, and surface engagements from a single location. Information flowed between ships through radio voice circuits, allowing formation commanders to build fleet-wide awareness of the tactical situation. By October 1944, a well-equipped American task force operated as a unified sensor and weapons system, each ship contributing to and benefiting from a shared understanding of the battle space that extended beyond visual range in all directions. The technical specifications were impressive. American SG radar used a frequency of 3,000 MHz with pulse lengths of 1 microsecond, providing range resolution of 150 meters, sufficient to distinguish individual ships in a formation. The rotating antenna completed 12 revolutions per minute, updating target positions every 5 seconds. The display systems used plan position indicators, essentially primitive radar screens that showed range and bearing of all detected contacts simultaneously, allowing operators to track dozens of targets and assess tactical geometry at a glance. Japanese radar systems, by comparison, operated at lower frequencies with longer pulse lengths, providing less precise range information and slower update rates. More significantly, Japanese ships lacked centralized information processing. Radar operators reported contacts verbally to the bridge, where visual plotting boards were manually updated. There was no equivalent to the American CIC, no integrated picture combining data from multiple sensors, no systematic method for maintaining continuous track on multiple targets maneuvering beyond visual range. As the Japanese center force steamed through the Cebuyan Sea on the morning of October 24th, these technical differences translated into operational reality with brutal clarity. American carrier task forces operating east of the Philippines had been tracking Japanese ship movements since the previous evening. Radar contacts plotted and updated continuously as the enemy fleet navigated through the San Bernardino Strait. American commanders knew the composition of the Japanese force, its speed, its course, its formation geometry, all derived from radar returns analyzed by trained CIC operators who could distinguish battleships from cruisers by radar cross-section and formation position. At 8:10 hours, the first American strike launched from Task Force 38's carriers. Dozens of aircraft vectored directly to intercept coordinates generated from radar tracking data. Japanese lookouts spotted the incoming formations with their characteristic excellence, but the warning came with insufficient time for effective defensive maneuvering. The Americans knew exactly where to find their targets because radar had tracked the Japanese fleet continuously through the night and dawn hours when Japanese visual reconnaissance could not function. Lieutenant Commander Nakamura, monitoring radio frequency emissions from Maya's intercept station, could hear the electronic evidence of American coordination. The radar pulses were accompanied by radio transmissions, fighter director circuits vectoring aircraft, surface coordination networks sharing contact information, all operating in clear, unencrypted voice communications because the Americans understood that speed of information flow mattered more than communication security when you possessed overwhelming technological advantage. The first wave struck at 10:26 hours. Nakamura felt the cruiser heel as Captain Kaname ordered emergency maneuvers. Through the portholes of his electronics compartment, he glimpsed aircraft diving through anti-aircraft fire, watched bombs and torpedoes track toward their targets with what seemed like impossible precision. Maya's Type 21 radar had detected the incoming strike at 60 kilometers, providing perhaps 6 minutes of warning. The American carriers that had launched those aircraft had tracked Maya continuously for 12 hours, updating her position every few seconds, knowing her speed and heading with precision sufficient to calculate intercept coordinates for aircraft launched from beyond the horizon. The disparity became even more apparent as the day progressed. American aircraft struck in wave after wave, each group vectored directly to the Japanese fleet's position by radar guidance. Japanese combat air patrols, launched in response to the attacks, struggled to find American carriers that remained beyond visual range, their location known to Japanese commanders only through imprecise radio direction finding. The few Japanese scout planes that located American task forces reported positions that were obsolete by the time strike packages could be assembled and launched. The Americans moved continuously, their location updated on Japanese charts only in discontinuous snapshots separated by hours. By contrast, American carrier groups maintained continuous radar track on the Japanese center force throughout its daylight transit of the Sibuyan Sea. When the massive battleship Musashi, pride of the Imperial Navy, with armor plate that could theoretically resist any weapon afloat, fell behind the formation after absorbing torpedo damage from the second wave, American strike coordinators knew immediately. Subsequent waves were directed specifically against the crippled giant, concentrating attacks against a target selected not through visual reconnaissance but through radar tracking that showed its reduced speed and separation from supporting vessels. The American tactical circuits monitored Nakamura, his English sufficient to comprehend the implications, if not every word. He heard American fighter directors vectoring combat air patrols toward incoming Japanese scout planes, intercepts executed with mechanical precision because the Americans could see both their fighters and the enemy aircraft on radar displays, could calculate intercept geometry and issue course corrections that brought American fighters to optimum attack positions. He heard surface coordinators repositioning picket destroyers, moving radar platforms to extend detection range, all coordinated through a network of radio and radar coverage that created a defensive zone hundreds of miles in diameter. As darkness fell on October 24th, the Japanese center force had been savaged but not destroyed. Musashi had sunk, taking over 1,000 men with her. Multiple cruisers and destroyers had suffered damage, but the core of the force, Yamato, the battleships Nagato, Kongo, and Haruna, heavy cruisers and screening vessels, remained operational. Vice Admiral Takeo Kurita, commanding the center force, made the decision to reverse course temporarily, withdraw toward the west, then turn again after dark and proceed through San Bernardino Strait under cover of night. It was a tactically sound decision based on traditional naval doctrine. Night had always been the great equalizer at sea, reducing engagement ranges to distances where Japanese optical superiority and superior night fighting training could compensate for daytime disadvantages. Japanese sailors practiced night combat extensively. Their lookouts trained to detect targets by moonlight or starlight. Their gun crews drilled in rapid engagement procedures against visually acquired targets. American forces, despite their technological advantages, were known to have struggled in night surface engagements earlier in the war. Kurita had reason to hope that darkness would negate American air superiority and reduce the battle to a gunnery duel where Japanese heavy ships might prevail. But October 1944 was not 1942. The American Navy that had struggled in night actions off Guadalcanal had learned its lessons and implemented technological solutions. By the time Kurita's force reversed course and headed back toward San Bernardino Strait, every major American surface combatant was equipped with SG surface search radar, capable of detecting ships at ranges beyond 20 kilometers in conditions of total darkness. More importantly, American destroyers and cruisers carried Mark IV and Mark VIII fire control radar that could track targets and generate firing solutions without optical sighting. At 0300 hours on October 25th, the Japanese center force emerged from San Bernardino Strait into the Philippine Sea. Nakamura, who had remained at his radar intercept station through the night, immediately detected the familiar pattern of American SG radar pulses. The signals were strong, indicating multiple transmitters at relatively close range, perhaps 30 to 40 kilometers. He reported to the bridge, "Multiple enemy surface search radar detected, bearing 090 degrees. Signal strength indicates range 30 to 40 kilometers." The report generated confusion on the bridge. Japanese optical lookouts, among the best in any navy, reported no visual contacts. The night was dark, but clear, visibility perhaps 10 to 12 kilometers. How could American ships be present at ranges where they should be easily visible to Japanese lookouts? The answer, which would become apparent with terrible swiftness, was that American ships were indeed beyond visual range, but not beyond radar range. The American vessels, a force of escort carriers and screening destroyers that had no business engaging battleships in surface combat, were tracking the Japanese force on radar and maneuvering to maintain distance while vectoring torpedo attacks. What followed was among the most confused and ultimately humiliating engagements in Imperial Navy history. Japanese battleships and cruisers charged toward enemy formations that appeared intermittently at the edge of visual range, only to fade back into darkness and smoke. American destroyers made torpedo runs guided by radar, launching from ranges and angles that would have been impossible to calculate using optical fire control. The Japanese fired thousands of shells, their optical rangefinders struggling to track targets that appeared and disappeared, that seemed to know exactly when to turn away and when to press attacks. Nakamura, listening to American radio circuits, understood what was happening even if the flag bridge did not. The Americans were fighting a radar-directed battle. Their destroyers were not bravely charging into visual range and hoping to survive long enough to launch torpedoes. They were executing carefully calculated attacks with radar-determined range, bearing, and target motion, launching weapons from positions that their radar told them would result in hits, then turning away before Japanese guns could achieve visual lock. The American carriers were not fleeing randomly. They were maintaining a radar-determined distance that kept them beyond effective gunnery range while allowing their aircraft to strike and their escorts to make torpedo runs. The battle off Samar, as this engagement would be known, lasted approximately 2.5 hours. When it ended, the Japanese had sunk 2 escort carriers and 3 destroyers, respectable tactical results against much lighter forces. But Kurita, unnerved by what seemed like coordinated attacks from all directions, convinced that he faced fleet carriers rather than escort carriers, because his intelligence picture was based on visual sighting reports and fragmentary radar contacts rather than the comprehensive tracking data available to American commanders, ordered a withdrawal. The center force turned away from the invasion beaches it had been intended to destroy, retired back through San Bernardino Strait, and ultimately retreated from Philippine waters. Japanese sailors could not understand how they had lost. They had more ships, bigger guns, heavier armor. They had fought with courage and skill, but they had fought blind against an enemy that could see them continuously, that could coordinate attacks and defenses with precision impossible when relying on visual sighting and manual fire control. Nakamura, reviewing his intercept logs in the days that followed, calculated that American radar had tracked Japanese ships continuously for over 30 hours through the multiple phases of the battle, night and day, through weather and smoke, at ranges from 70 kilometers down to point blank. Japanese radar, on the contrary, had provided intermittent detection at shorter ranges, sufficient to indicate enemy presence, but inadequate for the continuous tracking necessary for effective fire control or tactical maneuvering. The technical intelligence reports, produced by Japanese naval staff in the weeks following Leyte Gulf, made for grim reading. Analysis of American radar capabilities, derived from intercepted transmissions, captured equipment, and assessment of American tactical performance, revealed a technological gap of 3 to 5 years. American radar operated at frequencies Japanese equipment could barely detect, with pulse characteristics that provided precision and range resolution Japanese systems could not match. American integration of radar into fire control, fighter direction, and fleet coordination represented an operational philosophy that the Imperial Navy had not even attempted to implement. But the most damaging realization was not technical, it was strategic. Radar was not a piece of equipment that could be copied or developed through crash programs. Effective radar employment required trained operators, integrated combat information centers, coordinated doctrine, and, most critically, a cultural acceptance that electronic sensors could be trusted over visual observation. Japanese naval culture, with its emphasis on spiritual strength, intensive training, and fighting spirit, had no framework for understanding warfare where battles were fought against targets you could not see, where victory went to the side with better electronics and more effective information processing rather than superior seamanship or courage. The implications extended beyond radar. If American technological and organizational advantages in electronics were this pronounced, what about other fields? Japanese intelligence began reassessing American capabilities across the spectrum of military technology: aircraft production, naval construction, logistics, weaponry. The conclusions were uniformly discouraging. In almost every measurable category, American advantages were not being eroded by Japanese effort, but were expanding, as American industrial capacity and scientific establishment produced improvements faster than Japan could respond. Takeshi Nakamura, who survived the war and returned to Japan to witness its reconstruction, spoke carefully in post-war interviews about his experiences at Leyte Gulf. He described the sense of helplessness that came from monitoring American radar transmissions that revealed capabilities his own fleet lacked. He spoke of reporting to the bridge that Americans were tracking Japanese ships continuously and seeing that information have no tactical impact because Japanese commanders had no comparable capability to use the information effectively. He described the frustration of knowing the enemy's technological advantage, but being unable to translate that knowledge into countermeasures or tactical adjustments. "We knew they could see us," he said in a 1962 interview with an American naval historian. "We intercepted their radar signals. We understood that they were tracking our movements. But we had no way to become invisible to their radar, no way to jam their frequencies effectively, no way to fight a battle at ranges where our eyes were useless. It was like fighting a duel where your opponent can see in the dark and you cannot.
You may be the better swordsman, but if you cannot see your opponent, your skill means nothing. The interview took place at a technical conference in Tokyo, where Nakamura had become a senior engineer at a Japanese electronics firm producing radar equipment for the Japanese Maritime Self-Defense Force. The radar systems his company manufactured were based on American designs, licensed under technology sharing agreements established during Japan's post-war reconstruction. The irony was not lost on him. The defeated nation had adopted the victor's technology, the victor's organizational methods, the victor's understanding of how electronics and information processing could transform military operations. Takeshi Nakamura continued, "The Americans understood something we did not. They understood that modern war was not about individual ships or individual courage. It was about systems, networks of sensors and weapons and communications that worked together. One American destroyer with good radar was dangerous. A task force of American ships, all sharing radar data, all coordinating their movements and attacks, was almost invincible. We never thought that way. We thought about individual ships, individual battles. We lost before the fighting even started because we were fighting the wrong kind of war."
The radar signals that Takeshi Nakamura intercepted at Leyte Gulf were more than electromagnetic emissions. They were evidence of a fundamental transformation in naval warfare that the Imperial Japanese Navy had failed to recognize until it was too late. For 300 years, naval battles had been fought at ranges determined by human vision, battles won by ships that could see their enemies first, engage accurately, and maneuver effectively based on visual observation of the enemy's movements. Radar shattered that paradigm, extending the range at which ships could detect and track each other far beyond the horizon, enabling engagements in darkness and weather that would have been impossible in the age of optical warfare. But the transformation went deeper than simple range extension. Radar enabled a different way of thinking about naval operations. Traditional naval doctrine treated information as scarce and ephemeral. You saw the enemy for brief periods, made decisions based on incomplete information, and hoped your estimates of enemy position and movement were accurate enough to enable effective tactics. Radar-equipped forces operated in an environment of information abundance. You knew where the enemy was continuously. You tracked their movements in real time. You made decisions based on data that was seconds old rather than minutes or hours old. This shift from information scarcity to information abundance required more than just installing radar sets on ships. It required creating organizations that could process and utilize the information radar provided. The Combat Information Center was as important to American radar superiority as the radar sets themselves. Trained operators, standardized procedures, dedicated plotting equipment, and clear communication channels transformed raw radar data into actionable intelligence. Japanese ships had radar equipment, but they lacked the organizational infrastructure to use that equipment effectively. Radar reports were communicated verbally to the bridge, plotted manually on charts, and integrated into tactical decisions using the same methods employed in the pre-radar era. The Americans had reimagined naval operations around radar from the beginning. Fighter directors sat in CICs with radar displays, watching both their own aircraft and enemy formations, vectoring fighters to intercept positions calculated from real-time position data. Gunnery officers received continuous range, bearing, and target motion data from fire control radar, enabling them to maintain accurate solutions on targets they never saw optically. Formation commanders coordinated fleet movements based on tactical pictures derived from multiple radar sets, positioning their forces to maximize radar coverage and creating overlapping zones of detection that made it virtually impossible for enemy forces to approach undetected. This integration of radar into every aspect of naval operations was possible only because of the organizational model that had created the radar systems in the first place. The MIT Radiation Laboratory had operated as a collaborative environment where physicists worked alongside naval officers, where operational requirements informed technical development, where feedback from fleet operations drove iterative improvements.
The radar systems that tracked Japanese ships at Leyte Gulf were not static technology but continuously evolving equipment, with modifications and updates flowing from combat experience back to development laboratories and then out to the fleet in a cycle measured in months rather than years. Japan had lacked this organizational model. Radar development was fragmented across naval laboratories, army research facilities, and private manufacturers who competed for resources and rarely shared information. Operational feedback from fleet units rarely reached development teams. Cultural barriers between technical personnel and line officers meant that radar operators were often treated as technicians rather than tactical contributors, their reports given less weight than visual observations, even when radar provided more accurate information. In the final analysis, the story of Japanese radar at Leyte Gulf is not primarily about technology. It is about how military organizations adapt, or fail to adapt, to technological change that renders traditional doctrine obsolete. The Imperial Japanese Navy had been built on a foundation of visual warfare, intensive training in night fighting and optical gunnery, and a cultural emphasis on spiritual strength and individual courage. These were genuine strengths that had served Japan well in earlier conflicts, but they became weaknesses when facing an enemy that had fundamentally reimagined naval warfare around electronic sensors and information processing. The Americans understood that radar was not a supplement to traditional methods, but a replacement for them. Night fighting doctrine was rewritten around radar-directed gunnery rather than training sailors to see better in darkness. Fighter direction was reorganized around radar tracking rather than relying on visual coordination by flight leaders. Surface engagements were conceived as beyond visual range operations coordinated through radio communications based on radar tracks rather than flag signals and visual observation. Japan attempted to incorporate radar into its existing doctrine, to use radar to enhance traditional methods rather than replace them. The result was a hybrid approach that gained some benefits from radar but never achieved the full potential of the technology. Japanese ships with radar still fought primarily as visual warfare platforms, using radar for early warning but reverting to optical fire control for actual gunnery. Japanese aircraft carriers used radar to detect incoming raids, but lacked the fighter direction capability to vector interceptors effectively. Japanese destroyers equipped with radar operated individually, rather than as coordinated networks sharing sensor data. The Battle of Leyte Gulf demonstrated the consequences of this technological and doctrinal disparity with brutal clarity. Japanese forces fought with courage and skill, but they fought blind against an enemy that could see them continuously. Every tactical decision made by Japanese commanders was based on incomplete, outdated information, while American commanders operated with comprehensive, real-time awareness of the tactical situation. The outcome was never in doubt once the engagement moved beyond visual range into the realm of radar warfare, where American advantages were overwhelming. Takeshi Nakamura, listening to American radar pulses in the hours before the battle, understood intellectually that his fleet was at a profound disadvantage. But understanding was not the same as capability. The Japanese could detect American radar, could intercept American communications, could even analyze American tactical methods, but they could not replicate the organizational and industrial infrastructure that made American radar superiority possible. Radar sets could theoretically be copied, but you could not copy the MIT radiation laboratory, could not copy the industrial capacity that produced thousands of radar sets and trained the operators to use them, could not copy the cultural willingness to trust electronics over eyesight and to reorganize centuries of naval tradition around new technology. The radar signals detected at Leyte Gulf continued to echo through the remaining months of the Pacific War. As American forces advanced toward Japan itself, radar superiority became even more pronounced. American submarines used radar to detect Japanese shipping at night, attacking from beyond visual range with torpedoes guided by radar-derived firing solutions. American aircraft used airborne radar to locate targets through weather and darkness. American amphibious forces employed radar-directed naval gunnery to support landings with precision impossible using optical spotting. By 1945, Japan had no answer to American radar superiority. Attempts to develop improved radar systems were hampered by material shortages, bombing of industrial facilities, and the dissolution of effective communication between development teams and operational forces. The few advanced radar sets that reached the fleet came too late and in too few numbers to affect tactical outcomes. Japanese naval operations increasingly took place at night or in bad weather, attempting to exploit conditions where American radar advantages were reduced. But even this tactic had limited effectiveness as American radar continued to improve and Japanese forces became increasingly constrained by fuel shortages and the attrition of trained personnel. The intercept operators who had monitored American radar signals throughout the war produced a collective body of technical intelligence that documented the widening gap between Japanese and American electronic warfare capabilities. These reports, recovered after the war and analyzed by American and Japanese researchers, revealed that Japan had understood its technological disadvantages, but had lacked the resources and organizational capacity to address them. Japanese scientists and engineers were capable. Post-war careers would demonstrate that the talent existed. But Japanese military organization, industrial capacity, and strategic prioritization had failed to create an environment where that talent could produce effective wartime results. The post-war adoption of American radar technology by Japan's self-defense forces represented a tacit admission that the American approach to electronic warfare had been superior not just technically, but philosophically. The same organizational principles that had produced the SG radar and the Combat Information Center became the foundation of Japanese defense electronics after 1945. The transformation was dramatic and ultimately successful as Japan emerged as a leading manufacturer of radar and electronic systems in the decades following the war. But the transformation required abandoning cultural and organizational patterns that had defined Japanese naval operations for generations. The post-war Japanese Maritime Self-Defense Force operated American-designed ships with American-style CICs using American radar doctrine, not because Japan lacked the capability to develop alternatives, but because the American model had proven superior in every measurable way. The lesson learned at Leyte Gulf that
modern naval warfare required trusting electronics over eyesight, that coordination through information networks mattered more than individual ship capabilities, that technological advantage could render traditional skills irrelevant became foundational to post-war Japanese military thought. Takeshi Nakamura spent the final decades of his life working to ensure that Japanese forces would never again face the kind of technological blindness that had doomed the center force at Leyte Gulf. The radar systems his company produced incorporated lessons learned from both defeat and post-war collaboration with American firms. They emphasized integration, information sharing, and automated processing, all principles that Japanese naval radar had lacked in 1944. When he retired in 1974, Japanese Maritime Self-Defense Force ships carried radar and information systems comparable to any navy in the world, evidence that the organizational and cultural transformations forced by defeat had taken root and flourished. In his final interview before his death in 1981, Nakamura reflected on the moment when he had first detected American radar signals tracking the center force toward Leyte Gulf. "I knew in that moment that we would lose," he said quietly, "not just that battle, but the war. Because the signals I was hearing represented a way of thinking about naval warfare that we had not imagined. The Americans had not just built better radar, they had built a different kind of navy, one that fought battles we did not know how to fight. We could be brave, we could be skillful, we could sacrifice everything, and it would not matter because we were fighting in darkness against an enemy that could see perfectly." He paused, looking at the modern radar display in the corner of his office, a commercial navigation system that would have seemed like science fiction in 1944. But we learned. That is perhaps the most important lesson of all. Technology can be learned, methods can be copied, organizations can change. It took defeat to force us to learn, but we learned. The radar that tracks ships in Tokyo Bay today works on principles the Americans taught us in 1944 when they showed us what radar could do if you built your entire navy around it, instead of just bolting it onto ships designed for a different kind of warfare. The quiet hum of radar transmissions, the steady electronic pulse that Nakamura had first heard as an omen of defeat, had become in the decades after the war a symbol of technological and organizational renewal. The same signals that had tracked Japanese ships to their destruction at Leyte Gulf now guided Japanese vessels safely through crowded shipping lanes, coordinated search and rescue operations, and enabled the kind of information-based maritime operations that had once been an exclusively American capability. The radar still pulsed, still painted ships with invisible electromagnetic energy, still provided the continuous awareness that separated modern naval forces from their pre-radar predecessors. But the signals no longer divided the world into those who could see and those who fought blind. The lessons of Leyte Gulf, learned through bitter defeat, had been internalized and built upon, creating a new generation of naval forces that understood what Nakamura and his contemporaries had learned too late, that in modern warfare, information is as important as weapons, that electronic sensors can be more decisive than courage, and that the side that can see the enemy continuously will defeat the side that sees only intermittently, no matter how superior their traditional skills might be.
The dish antenna rotated, searching the electronic spectrum. The signals it detected were friendly now, part of a coordinated network rather than evidence of enemy superiority. But they carried the memory of that October morning in 1944, when a Japanese radar operator first understood that his fleet was steaming into battle already detected, already tracked, already defeated by an enemy that had reimagined naval warfare around technology his navy had treated as merely supplementary to the timeless principles of visual combat and individual courage.